This video is going to cover lecture 28. We are going to start off with a topic electronegativity and end this lecture with Lewis structures. Okay, so electronegativity, this is a new concept that we haven't talked about, and this specifically pertains to what is ionic versus molecular. So remembering ionic compounds, they are formed by the combination of our metals with our nonmetals, okay? And the ions are held together by this strong positive-negative charge electrostatic attraction called the ionic bond. The molecular compounds, as a review, it's formed by the combination of two or more nonmetals, and the atoms are held together by the covalent bond, where they're actually sharing the electrons in the bond. Now, the problem is the actual dividing line between what we say is ionic versus covalent, it's not as clear cut as I've been talking all semester long. Actually, many compounds, they have both ionic and molecular properties. So an American scientist, Linus Pauling, he won the Nobel Prize in Chemistry in 1954. What he did is he actually studied the nature of the chemical bond, and he came up with this concept that we use today. It's called electronegativity, and it's represented by En. So if you see En in the future, En represents electronegativity. So electronegativity is the ability of a bonded atom to pull or attract the electrons in the chemical bond toward itself. Now note, the higher the electronegative value, the more the bonded atom pulls the electrons in the bond toward itself. What you want to do is envision tug of war. Okay, so you have two people that are playing tug of war. The rope is going to represent the chemical bond, and the people represent the atoms. So one of the people, typically, when you're playing tug of war, is going to be stronger than the other person. So they're going to be pulling the rope more so than someone else. So this kind of pertains to what we're talking about here. You have two atoms, and there's a bond between them. One of the atoms is pulling the electron toward itself more so than the other, and it depends on their electronegative values. Now, in general, metals have low electronegative values. And why does that make sense? So metals, they don't want to share, they don't want to gain electrons. They're happily giving up their electrons in order to be like their closest noble gas. So they're not really pulling on on the electrons in a bond. They just happily give it up. So they have lower electronegative values. Nonmetals, now nonmetals don't want to give up their valence electrons. So that's why they produce these covalent bonds where they share the electrons in order to have that octet that we talked about. So nonmetals, they have higher electronegative values. They're going to be pulling the electrons more so than our metals. Now, an exception to this with the nonmetals are group 8A, the noble gases. They actually have electronegative values of 0. Remember, noble gases, they don't want to form compounds with anything else. They are happy. And now we know they're happy because they have an octet, making them more stable. Well, of course, except for helium. Helium doesn't have an octet. It follows the duet rule. And also xenon. Xenon, one of our noble gases, it has been known to react with fluorine. So you'll also see some compounds that have xenon, even though typically our noble gases don't form compounds with other species. How can we tell whether or not an element has a higher electronegative value than another? If I gave you the values, well, that would be pretty easy, but a lot of times you're not going to be given the values. What you're going to do is use a periodic trend to help you with this. So take a look at the periodic table here. The trend shows that as we go across a period, as we go across the table, the electronegative value increases. Noticing that even though as you go left to right, the values increase, the group 8A noble gases have electronegative values of 0. So actually, in the top right corner, not including the noble gases, we have fluorine. So fluorine has the highest electronegative value. And I know this because look at the left side here. It says that the electronegative value increases as you go up the table. So that means if you're going down, these will have lower electronegative values. Now, if you're given the electronegative values, you can use this information to determine the bond type. Now, what I'm going to tell you here, what we're going to be using to determine the bond type, this is actually an arbitrary guideline. It really depends on what textbook you use. You'll notice that if you look at different textbooks, you might see that the information is slightly different than what I have here. But this is what I'm going to be testing you on. So use this slide. Now you're going to be looking at the difference in the electronegative values of the atoms that are sharing the bond. So you're subtracting their electronegative values. So what we get here is called delta En. And then you compare delta En. If your difference in electronegative values is 2 or higher, we're going to call that an ionic bond. And so we know ionic meaning one species loses electrons, the other species gains. So ionic bond, and we know ionic bonds are stronger. I'm just going to make this a side note for ourselves. Just remember that. Then, if your delta En value is actually 0, so that means the two atoms that you are subtracting have the same electronegative value. We call that a nonpolar covalent bond. Now, we know what covalent bonds are, but what does the nonpolar part mean? Remember I described that with electronegative values in all of this, we're thinking of tug of war, okay? So the two atoms are sharing the electrons in the bond, and think of the bond as the rope. The two atoms are the people. And so if both people have the same strength, no one is winning tug of war. So when I was a student, I used to remember that as no one winning non-polar. Okay, so I used to think no one winning tug of war. So the atoms have to be pulling the electrons in the bond with the same strength. So they have the same electronegative value. If the delta En value falls between 0 and 2, we call that a polar covalent bond. So notice that these two are both covalent. What's different is I have a polar or a nonpolar bond. Now polar is kind of in between nonpolar and ionic. The tug of war example, with polar covalent bonds, I now have one substance that is stronger than the other. Someone is winning tug of war. Now they're still holding on to the rope, there's still that covalent bond and they're sharing the electrons, but one is pulling the electrons in the bond closer to itself. Now with polar bonds, this leads into the topic bond dipoles. So atoms with different electronegative values, but they're still sharing the electrons in the bond, so those polar covalent bonds, they're not sharing the electrons equally. So it says here they're going to share them unequally. And so the electron density will be uneven because one species is pulling the electrons closer to itself. In other words, you're going to have a higher charge concentration around the more electronegative atom. And this results in what we call a bond dipole. Now, bond dipoles indicate a delta notation. Now, the delta notation represents a partial charge. Remember ionic, you have metals giving up their electrons, forming the cation, and the nonmetals getting that electron or electrons, forming an anion, the negative charge. So here, they're not fully forming that positive and negative charge. They're forming a partial charge, okay, because they're still sharing the electrons in the bond. So take a look at the example right here of hydrogen fluoride. Okay, so and let's write the following notes about how to draw a bond dipole. What you first want to do is you want to draw an arrow towards the more electronegative atom. Okay, so my example here, I have hydrogen, I have fluorine, and I've already mentioned we know fluorine has the highest electronegative value. So I'm going to draw my arrow towards fluorine. Then, number 2, draw a vertical line on the opposite end. So in this example, my opposite end is on the side of the hydrogen. I'm going to draw my vertical line right here. Notice on this side, looks somewhat like a positive sign. And that's going to help you. This is the partial positive end, the hydrogen. So what does that mean? You do delta plus, and this represents partially positive. So number 3 in our notes here, let's put identify what is partially positive, so delta plus, and partially negative. On the right side, towards the fluorine, let me do this in green. If the positive end is towards the hydrogen, then the negative end must be towards the fluorine. So notice we have the partial negative or delta negative on the fluorine end. Now what does this represent? So let's put in here partially negative. Okay, so going back to cations, anions. Cations, positive charge, representing loss of electron. Anions, a -1 charge, represent you're gaining an electron. So here, my hydrogen partially is losing the electron in the bond because the fluorine is pulling the electrons in the bond closer to itself, so it partially or kind of gains the electrons. So it's partially negative. Let's look at another example. Let me do this in black. What if I had a bond between phosphorus and chlorine? So take a look at the periodic table. Just use the periodic trend. Now phosphorus and chlorine are both in period 3. So I'm going to use the trend that as we go from left to right, the electronegative value increases. Therefore, chlorine is going to have a higher electronegative value. And going through my 3 steps, number 1, draw an arrow towards the more electronegative atom. Chlorine has the higher electronegative value, so I'm going to draw that arrow towards chlorine. And then on the opposite end, I'm going to draw a vertical line down. So that symbol right there represents, this right here, represents the bond dipole. Now let's identify what's partially positive and partially negative. And let me change this back to red. Okay, so this end right here, it helps you out that it looks somewhat like a positive charge. So this is my partial positive end, and the chlorine is the partial negative end. Now again, what does that represent? It represents that phosphorus is partially losing the electrons in the bond to chlorine. And chlorine, since it's stronger, pulling the electrons in the bond closer to itself, it's partially gaining the electron. Now, does chlorine fully gain the electrons? No, because phosphorus is still holding on. It's just weaker. Now let's take a look at some practice problems. So here it says, what type of bonds are present in each of the compounds shown below? And in this exercise, I've given you all of the electronegative values. Now it does say, if it forms a polar covalent bond, indicate which atom has the partial negative and which the partial positive charge. Let's start with calcium oxide. So what I would do is I would look up the electronegative values of calcium and oxygen. So calcium has a value of 1.1, so I'll just write that above, 1.1. And oxygen's value, let's see, let's look it up, there it is, 3.5. So delta En is equal to the absolute value of just subtracting these values, 1.1 and 3.5. So delta En, when I subtract, I get 2.4. So now I use that arbitrary guideline a few slides back, and I see that if I have a delta En value 2 or greater, it is considered an ionic bond. Now hopefully, when you started this exercise and you saw calcium oxide, I hope you were initially thinking, oh, that's got to be ionic. Calcium is a metal, oxygen is a nonmetal. And you are correct. It is an ionic bond. The next one, I have methane or carbon tetrahydride. So we're just looking at one of those carbon-hydrogen bonds. I'm going to look up the electronegative values from above. Carbon's is, let's see here, 2.5, and hydrogen's value is 2.1. So now I'm going to subtract those numbers to get delta En. So the absolute value, we don't want any negative numbers. So delta En is equal to 0.4. I use my arbitrary guideline. I notice that 0.4 is in between 0 and 2. So that would result in a polar covalent bond. So they're sharing the electrons, but they're not sharing them equally. So it says in the instructions, if you get a polar covalent bond, let's draw the bond dipole representing what's partially positive, partially negative. So down below here, let's draw the carbon bonded to the hydrogen. I would look at the periodic table if I wasn't given the actual electronegative values. However, in this exercise, they give me the values, so I know which atom has the higher electronegative value. In this case, it's going to be carbon. Now I could use the periodic trend, seeing that carbon is further to the right on the periodic table than hydrogen. Now actually, hydrogen, even though it's a nonmetal on the left side, you actually can insert hydrogen between boron and carbon on the table. So just a little side note there. Okay, so carbon has the higher electronegative value, and then we draw the arrow towards the carbon and then the vertical line on the opposite end. And so I can see here, this looks like a positive, okay, end towards the hydrogen. So that's my delta positive, and carbon is delta negative. Carbon partially gains an electron from the bond, and then hydrogen partially loses. The next one is chlorine. And so this is going to be your participation question for today. So what type of bond is in this chlorine molecule? And so if you're applying the electronegative values and subtracting them, where does it fall? Is it a non-polar covalent bond? Is it a polar covalent bond? Or is it an ionic bond? All right, the sulfate, I'm just looking at a sulfur-oxygen bond. So looking up the electronegative values, sulfur's is 2.4 and oxygen's is 3.5. So let's calculate delta En. So 2.4 minus 3.5 gives me a delta En value of 1.1. And in my guideline, it shows that this would be a polar covalent bond. And now we have to draw the bond dipole. Remember, you only have to draw a bond dipole if you have a polar covalent bond. And why? Because the bond dipole represents the unequal sharing of the electrons in the bond. So I have sulfur and oxygen bonded with a covalent bond. And I know from the electronegative values, oxygen has a higher En value than sulfur. So I'll draw the arrow towards oxygen and then the vertical line on the opposite end. And so sulfur will have that partial positive end and oxygen partially negative. And the last example, now zinc and sulfur. If I were to ask you right now, what do you predict? I have zinc, a metal, sulfur, a nonmetal. I hope you would say you'd predict that this would be an ionic bond, right? Metal and nonmetal. Let's take a look. So zinc's electronegative value is 1.7 and sulfur's is 2.4. Calculating delta En, I'm going to subtract my numbers here and get a delta En value of 0.7. So instead of it being ionic, this is showing me that zinc and sulfur bond is polar covalent. They're actually sharing the electrons in the bond versus zinc giving up its electrons and sulfur taking it. So here's an example where I mentioned earlier the actual dividing line between ionic and covalent compounds is not so clear cut. Here's an example. You would think this would be ionic, but actually zinc and sulfur form a polar covalent bond. So let's draw the bond dipole between zinc and sulfur. I know that sulfur has the higher electronegative value, so I'm going to draw an arrow towards sulfur, draw the vertical line down on the opposite end, and that shows me zinc has a partial positive charge and sulfur has a partial negative charge. Now my next question would be, of all the polar covalent bonds, and let's do this in blue, I have a polar covalent bond here between the carbon and hydrogen, the sulfur and oxygen, and the zinc and sulfur. Let's ask another question. Which is more polar of those three polar covalent bonds? So let's remind ourselves. We have the CH bond, and the CH bond's delta En is 0.4 from above. We also have the sulfur-oxygen polar covalent bond. Its delta En value is 1.1, and the zinc-sulfur bond, the delta En value is 0.7. So the higher the delta En value, the more polar that bond is. Look at the example here. Let's compare the delta Ens. I see that my sulfur oxygen, let's do this in green. My sulfur oxygen has the highest delta En. So let's make note of the following. Okay, so the higher the delta En, the more polar it is. And polar, we're thinking unequally sharing the electrons in the bond. Okay. Let's take, for example, let's compare the carbon-hydrogen and the sulfur-oxygen bond. Okay, so the carbon-hydrogen bond, the delta En value is 0.4. It's pretty small. It's almost non-polar covalent, but it isn't. It's polar covalent. It would almost be like me in a tug-of-war match with someone of equal size and almost equal strength, maybe someone that's slightly weaker than me. Versus the sulfur-oxygen bond has a higher delta En value, so that would be like me in a tug-of-war match with my 7-year-old daughter. Hopefully I would win that match, and I like to think that I'm much stronger than her. Hopefully that helps you with understanding what that delta En represents. The higher the delta En, the more they are not sharing the electrons equally in that bond. Now that we've done Lewis dot symbols in the previous lecture, let's get into more complicated compounds. And so this leads into Lewis structures. So we use Lewis dot symbols to show the arrangement of valence electrons such that they obey the octet rule, at least the ones that do obey the octet rule, because we know that some of them just don't. So an example here, it says draw Lewis structures for fluorine, oxygen, and nitrogen. Okay, so fluorine, if we draw the Lewis dot symbols of fluorine and another fluorine, well, we know that the valence number, fluorine has 7 valence electrons because it's in group 7. So I'm going to draw the 7 valence. Now, remember we put 1 dot on each side of the box and then we pair them up. But I already know that 3 sides of my box will have 2 dots and 1 will have 1. So I have another fluorine where I'm going to put 1 dot on one side and 2 dots on the other 3 sides. And I'm drawing it this way so we can really see that covalent bond forming. Now fluorine wants 1 more electron in order to achieve that octet, right? Because right now it has 7 valence electrons, it wants 8. And each fluorine wants 1 more to do this. And we know fluorine's not going to give up its electrons. It has a really high electronegative value. So instead, each fluorine is going to share an electron with the other. And it's going to form that covalent bond, and we represent that with a line. The line represents the 2 electrons in the bond. And then we also have to show those electrons that are not bonded, those other valence electrons. So that would be the fluorine molecule. Now take a look at just this fluorine right here. Count up the electrons, the valence electrons around that fluorine. So I'll mark over with the blue. I have 1, 2, 3, 4, 5, 6, and then the 2 in this bond, 7, 8. So that fluorine obeys the octet rule, and it should, because fluorine does want to obey the octet rule. If I do the same for this fluorine, counting up all the valence electrons, 1, 2, 3, 4, 5, 6, and then the 2 in the bond, 7, 8. So that fluorine also obeys the octet rule. Let's do oxygen as the next example. And so the Lewis dot symbol for oxygen, oxygen's in group 6. It has 6 valent electrons. So 2 sides will have 2 dots. And 2 sides will have 1 dot. Now I'm going to draw it this way so we can, again, see the covalent bonds a little bit more clear. So each oxygen has 6 valent electrons. In order to achieve the octet, it needs 2 more electrons. Since they can't gain the electrons, because both oxygens don't want to give up their valence electrons, they're going to share. But not just 1 pair, they have to share 2 pair. And so let's draw the Lewis structure. I have 2 oxygens, but now I formed a double bond. And then we draw those 4 valence electrons that are not bonded. I put them in diagonals because electrons are negatively charged, as we know, and they really don't want to be near each other. Then they can be together as a pair, but the pair want to be as far apart as they can be from the other electrons. So I put them in diagonals. You don't have to put them that way, but we typically put them in diagonals here when we have that double bond. And so there's my oxygen molecule. Let's count up and make sure each oxygen obeys the octet rule. Let's look at this oxygen first. Let's count up. We have 1, 2, 3, 4, 5, 6, 7, 8. So the double bond consists of 4 electrons that are being shared. So yes, that oxygen obeys the octet rule. And if you count up the other oxygen, you would notice again, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons surrounding it. So they both obey the octet rule. The nitrogen is our last example. So I have 2 nitrogens that are bonded together. Nitrogen's in group 5, so it has 5 valent electrons. So 3 sides will have 1 dot, and 1 side will have 2 dots. And so each nitrogen needs 3 more electrons in order to achieve that octet. So what it's going to do is it's going to share 3 pairs of electrons. So let's draw the Lewis structure correctly by putting 3 lines in between to represent that triple bond. And then I have a pair of electrons remaining on each nitrogen that are not bonded to anything else. Let's see if it obeys the octet rule that we did this properly. Let's look at this nitrogen here. Let's count up. There are 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding that nitrogen. And if you look at the other nitrogen, you would see again 8 electrons surrounding it. So yes, both nitrogens obey the octet rule. Now B, it says, let's define the following terms. So a single bond is when you're sharing 1 pair of electrons, and so that would be our fluorine example, where we have a single bond between the 2 fluorines. A double bond where you're sharing 2 pairs of electrons, so that would be our oxygen example. And then the triple bond sharing 3 pairs would be the nitrogen example. Some other terms. Bonding electron pair, that would be the covalent bond. These are the electrons that are shared between the two atoms. So examples, this would be my bonding electron pair. Here are bonding electron pairs. Here's 3 bonding electron pairs. But we also have to know what are the non-bonding, also known as lone pairs of electrons. Typically, I will call it the lone pairs of electrons. These are the electrons that are not shared between the two atoms. So here, those 2 electrons on that nitrogen would be my lone pair of electrons. Here's another pair. Here's another lone pair, lone pair, lone pair, lone pair, lone pair. I could keep going, okay? And then we've already talked about bond order when we talked about bond length and bond energy. So bond order is the number of pairs of electrons shared between the 2 atoms. So with my fluorine example, I would have a bond order, so I'll put BO. I have 1 shared pair, so we know that would be a bond order of 1. 2 shared pair, bond order of 2, and 3 shared pair would be a bond order of 3. So how do we draw Lewis structures? Before I move on, I'm going to ask that you please follow these steps. I find that students want to start off with the Lewis dot symbols, kind of like what I did in the last slide, and then from there create their Lewis structures, and it really makes things complicated. Just follow these 7 steps, okay? And if you follow these 7 steps, drawing Lewis structures will not be difficult. So let's start with number 1. First, you're going to count up the total number of valence electrons of everything in the compound, okay? Then determine the skeletal structure. So what's bonded to what? Now the central atom is usually written first in the chemical formula. However, hydrogen can never be a central atom. And with our acids, hydrogen will be written first. So keep that in mind. Even if hydrogen's written first, you know it can't be a central atom. First, you're going to be placing 2 electrons in each bond. Then surround the non-central, okay? Worry about your outer atoms. Surround the outer atoms, the non-central atoms, by an octet of electrons. Make them happy because they want an octet. Except hydrogen. Again, hydrogen is an exception. It follows the duet rule. It's happy with 2. Then you count up how many electrons remain. Place any remaining electrons on the center atom. And you put them on the central atom as an electron pair. If the central atom does not have an octet, and it wants to form an octet, okay, because some don't obey the octet rule, but if it obeys the octet rule, you're going to have to form the double and triple bonds. You'll form the multiple bonds to give it their octet and make them happy. Hydrogen, boron, beryllium, fluorine, and your metals do not generally form multiple bonds. Now, if the central atom in step 6 does not form multiple bonds, you're just going to leave it short of electrons. Okay? So let's do some practice problems. Our first example here is CH4, carbon tetrahydride, more commonly known as methane in organic chemistry. First step is we have to determine the number of valence electrons, total. So I'm going to divide it up. I've got carbon, and we'll do this in red. So carbon, valence electrons, it's in group 4, so it has 4 valence electrons, and there's only 1 carbon. So 1 times 4 valence, 4. Hydrogen, there's 4 of them in this compound, and hydrogen's in group 1, so it has 1 valence electron. So 4 times 1, a total of 4 from the hydrogens, and then I'm going to add everything up, and I have 8 electrons to distribute, no more, no less. Starting with the skeletal arrangement, before we can start adding the bonds, I have carbon written first. Typically elements written towards the left side of the periodic table, the more left you go, I guess basically is what I'm trying to say. They typically want to be in the center, except for hydrogen. Remember, hydrogen can never be in the center. So carbon's in the middle, surrounded by 4 hydrogens. So here's my skeletal arrangement. Now I drew them this way just because, I don't know, I like to make them evenly spaced around the carbon. We're going to figure out later this is not actually the way it looks. But for Lewis structures, it's fine. We'll get into the actual shapes later. The next step, it says to go ahead and put 2 electrons combining the atoms together, forming a covalent bond. So here are my 2 electrons between the carbon hydrogen, 2 electrons, 2 electrons. So I'm connecting them with a single bond. Now, how many electrons have I used up? I've used up 2, 4, 6, 8 electrons because, again, in each bond there's 2 electrons. I've used up all 8. Remember, I only have 8 electrons, so I'm done. Now, check that each atom is happy. If it obeys the octet rule, it needs to obey the octet rule, okay? Carbon has to obey the octet rule. And sure enough, it has 8 electrons surrounding it. Hydrogen obeys the duet rule. And each hydrogen has 2 electrons around it, coming from the chemical bond, right? So this is the correct structure for CH4. Now the next molecule, carbon monoxide. Let's add up the number of valence electrons total. So there's 1 carbon, and we know carbon's in group 4, so 4 valence. Oxygen's in group 6, so it has 6 valence electrons. And if I add everything up, I have 10 valence electrons. Now, the skeletal arrangement for CO is pretty easy because there really isn't a central atom. I'm actually going to draw this up top here so I have more room. Okay, so I start by just connecting the 2 atoms together with a single bond. Then it says, give the outer atoms their octet. Make them happy. Now, I don't really have a central atom because I only have 2 atoms in this compound. So just pick an atom and make it happy. I'll pick oxygen. Okay, you could have picked carbon. Make oxygen happy. Well, right now, oxygen has 2 electrons surrounding it. It needs 6 more because it wants to have an octet. So let's put 6 more electrons around the oxygen. And you're still envisioning that box, okay? And putting 2 electrons on each side. So now I've used up 2, 4, 6, 8 electrons, and I only have 10. I have 2 left over. I'm going to go ahead and put them on the carbon. I have no more electrons. Now take a look. Would this be the correct Lewis structure? I hope you would say no, because carbon does not obey the octet rule here. Carbon only has 4 electrons around it, 2 here and 2 from the bond. So carbon has to obey the octet rule, but I have no more electrons to give out. This is when you form multiple bonds. Now don't go straight to a triple bond. Go from a single bond, next try a double bond, okay? So I'll take my carbon and my oxygen, instead of a single bond, let's connect them with a double bond. So we're starting all over again. Pick one of the atoms, make them happy. Make it happy. So the oxygen already has 4 electrons from the double bond. It needs 4 more electrons to be happy. So I'm going to give it the 4 more electrons. So I've used up 2, 4, 6, 8 electrons. I have 10, 2 left over, just like in the last example. I'm going to put them on the carbon. Now, is everything happy? Well, we know oxygen's happy, but carbon still isn't happy. Carbon only has 6 electrons around it. So that's when you try a triple bond. We know with single, double, triple bonds have more energy than single bonds. So again, that's why you don't go straight from a single bond to trying a triple bond. Make sure the double bond doesn't work before moving on to a triple bond. So try the carbon, oxygen connected with a triple bond, okay? And so my oxygen needs 2 more electrons because it already has 6 from the bond. So I'll give it 2 more electrons. I've used up 8 of the 10 electrons. I have 2 left over. So I'll put them on the carbon. And then I double check. Oxygen we know is already happy, but let's look at the carbon. Carbon now has 2, 4, 6, 8 electrons around it. So this is the correct Lewis structure for carbon monoxide. Next, let's do carbon dioxide. Let me switch colors here so the reds don't bleed into one another. Okay, so CO2, let's count up the valence electrons. I'll do this up top. Carbon, one of them, 4 valence electrons, so 4. Oxygen, there's 2 of them in this compound, and each oxygen has 6 valence, so a total of 12. So when I add up my numbers, I have 16 electrons. Now the skeletal arrangement, carbon is written first, and also, carbon's further to the left on the periodic table, so it tends to want to be in the center anyway. And actually, there's a whole field of chemistry dedicated to carbon, especially carbon being in the middle, and that's organic chemistry. So carbon being in the middle is very common, and I'm going to surround it with 2 oxygens. Now with our steps, we're just going through step by step. We have the skeletal arrangement. Next, connect the atoms with a single bond. So let's do that. Then give your outer atoms, the non-central atom, their octets. So give the oxygens an octet, make them happy. So each oxygen already has 2 electrons from the bond. So give each oxygen 6 more so that they have their octet. By doing so, I have used up all 16 electrons. And hopefully you can see something's not right here. My carbon only has 4 electrons around it. And we know carbon obeys the octet rule. So this is where we try a double bond. Pick a side, any side, doesn't matter. And instead, give it a double bond. So I just picked the right side, you could have picked the left side, and that's fine. Give the outer atoms their octet. Okay, remember you're always going to be focusing on that central atom last. The oxygen on the right already has 4 electrons from the bond, so it needs 4 more electrons. The oxygen on the left already has 2 electrons from the single bond, so it needs 6 more to achieve that octet. And again, I've used up the 16 electrons. Carbon still isn't happy. Carbon only has 6 electrons around it. Now don't go straight to a triple bond. You can try 2 double bonds in this example. Squeeze this in. So 2 double bonds. And carbon, double bond to oxygen. And so each oxygen now needs 4 electrons. And that is the correct Lewis structure for carbon dioxide, since both oxygens and the carbon all have an octet. The next molecule, nitrogen trichloride, okay, we're going to add up, let's do this in green, the number of valence electrons. So nitrogen in group 5, so 1 times 5, 5 electrons. Chlorine, there's 3 of them. It's in group 7, so 7 valence, so a total of 21 electrons, since there's 3 of them. And if I add everything up, I have a total of 26 valence electrons. Skeletal arrangement would be next. Nitrogen written first, central atom, surrounded by 3 chlorines. And I'm going to first connect them with a single bond. Okay. And then I'm going to focus my attention on the outer atoms. Do not focus on the central atom next. Worry about the outer atoms, the chlorines in this example. Make them happy. Give them their octet. So each chlorine would need 6 more electrons. Okay, so if I count up all of the electrons, the 2 electrons in each bond and all of the lone pairs of electrons, I have distributed 24 electrons. I have 26, so I have 2 left over, and so I'm going to put them on the central atom. Now check to make sure everyone is happy. The nitrogen's happy. Nitrogen has 2, 4, 6 from the single bonds, and then the 2 lone pair, a total of 8 electrons around it. Each chlorine has its octet, so this would be the correct Lewis structure. All right, the next example we have here is a species that is charged, ClO2 with a positive charge. Okay, let's first count up the total number of valence electrons. Chlorine, there's 1 times valence number of 7, so 7 valence. Oxygen, there's 2 of them, 6 valence electrons, 12. So when I add up, I get 19 electrons, but because it has a positive charge, we know positive charges meaning losing electrons, in this case 1, because it's a positive 1 charge. So really I have 18 electrons to distribute. The skeletal arrangement would be next. I have the chlorine in the middle, it's written first. So I'll put a chlorine here, surrounded by 2 oxygens. And I'm going to start by connecting them with a single bond. Then focus your attention on the outer atoms, the 2 oxygens. Make them happy. Let's give each oxygen 6 more electrons. Now I have used up, let's see here, 2, 4, 6, 8, 10, 12, 14, 16 electrons, but I have 18 to distribute, 2 left over. Let's put them on the central atom. Now, this is the first time we're seeing a charged molecule. When you have a charged molecule, in this case, this has a positive charge, you have to put the Lewis structure in brackets with the overall charge in the upper right corner. Now, is this the correct structure for ClO2+? Notice the chlorine does not have an octet. It only has 6 electrons surrounding it. So what do? We don't have any more electrons, so we're going to have to try a double bond. Chlorine, 2 oxygens. Now on one side, go ahead and put a double bond. Doesn't matter what side. Focus your attention on the oxygens. Give them their octet. So this oxygen on the left needs 4 more, and the oxygen on the right needs 6 more. And so I've used up 16 electrons. I have 2 left over, so I put them on the central atom. And then I check, is everything happy? The 2 oxygens are happy, and now the chlorine is happy. Chlorine now has an octet around it. So this is the correct Lewis structure, but we can't forget, put it in brackets with the charge in the upper right corner. Okay, so I think I'm going to end with this problem today. If I finished up the rest of the molecules on the slide, this lecture video is going to be well over 1 hour. And so I try to keep them around 50 minutes. So we'll pick up on this next molecule at the beginning of lecture 29.